So you probably think you know the simple number line, right? Well, today, in this explainer, we're going to completely shatter your preconceived notions about it. We're stepping into a mathematical sandbox where absolutely no fractions are allowed, just whole integers. But I gotta warn you, this basic counting tool we all grew up with, it's actually a masterclass in deception.
Because we're so familiar with these numbers, we just kind of assume we've mastered them. But what if I told you that the exact same numbers you used in kindergarten to count wooden blocks actually hide infinite, unpredictable patterns? Patterns that literally continue to terrify and baffle the world's absolute greatest mathematicians.
I mean, on the surface, integers just look like boring, evenly spaced dots on a flat, one-dimensional line. You've got 0 right there in the middle, and then counting numbers stretching out infinitely in both directions. It feels incredibly safe, completely ordered, and frankly, just a little bit plain. After all, there is absolutely nothing, no hidden fractions, no decimals, between 0 and 1 in this universe.
All right, let's move into part 1, the hidden prime DNA. Because here's the thing, when we shift our perspective away from basic addition and start looking at multiplication, that smooth, predictable number line completely shatters. We start to discover this hidden, underlying structure. And prime numbers, they are the architectural matrix of this whole system. Thanks to the fundamental theorem of arithmetic, we know that primes act as the fundamental multiplicative building blocks. They're basically the chemical atoms of all natural numbers. Every single integer greater than 1 is either a prime itself, or it's uniquely constructed by multiplying primes together.
This means every composite number breaks down into a completely unique DNA sequence of these prime factors. Take a number like 4312, for example. To the naked eye, it's just your standard 4-digit number, but its true underlying blueprint is actually 2 cubed times 7 squared times 11. That specific, exact combination is literally the only way to build 4312 using multiplication. It's like a unique fingerprint. And once you see this, you stop viewing integers as just a sequence of simple counting steps. You actually start seeing them as complex molecules.
And when you map out these prime factors, it reveals how seemingly distant, totally unrelated numbers on our flat line are secretly tangled together behind the scenes. If you were to take the prime factors of, say, 36 and 90 and put them in a Venn diagram, you can visually see their hidden mathematical relationship. Just like that, abstract division instantly turns into this beautiful visual map of intersecting sets. Notice how these overlapping primes create these incredibly beautiful symmetries. These shared building blocks actually govern things like the greatest common divisor and the least common multiple, which are mechanics we're really going to explore deeply as this series continues. But for now, just marvel at this perfect invisible ecosystem operating right beneath our noses. The math just elegantly balances out, proving for sure that there's a deep, structural rhythm to the integers that you just cannot see on a simple flat line.
Which brings us to part 2, geometry of numbers.
Now think about how crazy this is. To truly understand these flat, one-dimensional counting numbers, pioneering mathematicians like Hermann Minkowski realized we actually have to pull them out into a higher dimensional space. He treated algebraic integers as a multidimensional lattice embedded in Euclidean space. So instead of just running endless boring arithmetic, we can actually answer deep questions about number theory by looking at physical shapes, volumes, and geometric grids.
Imagine how this translates visually. When we're looking for integer solutions to complex equations, we aren't just crunching numbers in our heads anymore. We're actually checking if a specific straight line perfectly pierces the intersections of a physical grid, kind of like lining up crosshairs on a piece of graph paper. The flat number line actually projects outward into this beautiful hidden geometry.
All right, moving on to part 3, the unpredictable prime distribution.
Because the deeper we go into these integers, the more the rules of predictability just begin to break down entirely. They hide some wildly irregular and chaotic behaviors. But, and this is the wild part, if you take that flat number line and you wrap it around itself into a square spiral, and then you highlight only the prime numbers, you don't just get random static, you actually get distinct, bizarre diagonal stripes. It's known as the Ulam spiral. And it's this tantalizing hint that even in the absolutely most chaotic parts of mathematics, there's a hidden architectural blueprint just waiting to be found.
And that leads us perfectly into part 4, unsolved integer mysteries.
See, the ultimate illusion of the integers is that they feel completely figured out, like a closed textbook. But actually, they are full of dark corners we haven't even mapped yet. Just take Goldbach's conjecture. It's a puzzle that is literally simple enough for a child to test. 4 is 2 plus 2.
6 is 3 plus 3. 8 is 5 plus 3. It works every single time you try it. Modern supercomputers have verified it for staggeringly huge numbers, yet absolutely no one, no mathematician in history, has been able to mathematically prove that it holds true for infinity.
We've peeled back just a single layer today in this explainer, moving from a flat, simple line of counting beads to a multidimensional lattice full of secrets. So as we wrap up and look ahead to exploring exactly how these integers interact, ask yourself this. If the simplest numbers we know hold mysteries that continue to completely stump the greatest minds on Earth, what else is hiding in the infinite?